Hey, this is Chemistry Chapter 13, the fourth and final lecture for this chapter. In the book, this material starts on page 446. And what we're going to talk about today is Gibbs free energy. So Gibbs free energy is a mathematical mechanism to determine whether or not a reaction, a chemical reaction, can occur. Because if a reaction violates the second law of thermodynamics, it won't occur. Okay, so if it does occur, if a reaction doesn't violate the second law of thermodynamics, we call it a spontaneous reaction. So that can occur, doesn't violate the second law. Okay, so if it does violate the second law, it would be non-spontaneous. Okay, just the opposite there. Okay, so we've got a couple of equations that we're going to use to try to determine both what temperature ranges that a reaction can occur that will cause a reaction to be spontaneous. And then also we'll use a table to determine the Gibbs free energy. But this is a key concept in that Gibbs free energy, so we'll call that delta G, must be negative for a reaction to be spontaneous. Okay, so we're going to do some math, and if we get a delta G that's negative, we know that the reaction is spontaneous, or it's just a fancy way of saying that it can occur. Okay, here is the equation that you need to memorize when we're working problems that ask for temperature range. All right, that's delta G, Gibbs free energy, is equal to delta H minus T delta S. Okay, delta H is enthalpy. We've worked with that. Delta S, entropy. And the temperature must be in Kelvin. So when we work problems and we get a temperature range, the units will be in Kelvin. All right, so let's look at 13.11. on page 449. That says the delta H of a certain chemical reaction is 10 kilojoules, whereas delta S is 123 joules per Kelvin. At what temperatures is this reaction spontaneous? Okay, so we're going to use this equation, delta G is equal to delta H minus T delta S. We know that G must be negative. Right? Delta G must be negative. So in order for this quantity to be negative, we're going to make an inequality here. 0 is greater than delta H minus T delta S. If that's the case, if 0 is greater than something, then this part is going to be negative. So we have 0 is greater than, all right, delta H from the problem is 10 kilojoules. I'm not going to put the unit, okay, until the end. And then minus T, we're solving for T, solving for a temperature range. It says delta S is 123 joules per Kelvin. We've got to change that to kilojoules. All right, we've got to change 123 joules to kilojoules. So that's 0.123 kilojoules per Kelvin. That's a really common mistake to mix up the units. All right, so we've got 0 is greater than 10 minus 0.123 T. All right, I am going to add 0.123 T to both sides, so I'd have 0.123 T is greater than 10. Okay, let's pull this up here. Then T is going to be greater than 10 divided by 0.123. So T would be greater than 81.3 Kelvin. So if it gets colder than 81.3 Kelvin, then this reaction won't go, this particular reaction. But as long as it's warmer than 81.3 Kelvin, then this reaction is spontaneous. So let me give you one warning. If you set your inequality up that somewhere in there you are dividing by a negative, remember you have to flip the inequality. I have a tendency to try to make it to where I don't do that so I don't forget to flip. But if we had moved this 10 to the left and made it negative 10 and then divided by negative 0.123, then we would have had to flip the inequality. We would have had to flip that. So remember that algebraic rule, if you divide by a negative, you've got to flip the inequality. All right, I'm going to erase and we'll move on to the last on your own problem of this chapter. So let's say we have a reaction at 298 Kelvin, which is considered room temperature. Then we can actually use the table of values that scientists have put together to figure out the delta G. So our equation, so we're moving on to page 7 in your notes. Okay. Our equation is delta G is equal to the Gibbs free energy of formation of the products minus the Gibbs free energy, and it's a sum. Sorry about that. All right, there's a lot of little symbols, standard conditions, formation, all that, but don't worry about all that. It's not really, it's just like the enthalpy and the entropy equation. You just add up the products and subtract out the reactants and use the table. We're going to be using table 4 on your sheet. Okay, and you know, just look at the title, standard Gibbs free energies of formation in kilojoules per mole. Okay, so if you're in a Gibbs free energy problem, then use table 4. All right, on your own 13.12 says, is the following synthesis of ethyl alcohol a spontaneous reaction at 298 K? Well, let's write out the reaction. All right, we've got methane plus oxygen, and that makes C2H6O liquid plus liquid water. Okay, it's already balanced for us, so let's figure out delta G from the table. So I've got 1 mole, again we're doing products minus reactants, 1 mole of C2H6O liquid. Looking at our table, right, that is right there, and it's negative 175 kilojoules per mole. We're going to add to that liquid water. We've got 1 mole of that. Liquid water from table 4 is in the second column of substances, negative 237. And then we want to subtract out the 2 reactants. So we have 2 moles of CH4 gas. Okay, we're right there. 2 moles of CH4 gas. That is the very first one. It's a negative 50.8. And you'll notice that O2 is not in the table. That's because just like enthalpy, the Gibbs free energy of formation of an element, single element in its elemental form, so it's O2 is normally how oxygen exists in the atmosphere, is 0. Okay, so minus 0. So delta G is going to be negative 175 minus 237 plus 2 times negative 50.8, and minus would make it a plus, 101.6. And that'll give you a negative 310.4 kilojoules. So that's the Gibbs free energy. Is this reaction spontaneous? It is yes, because delta G is negative. If it were positive, then this reaction would violate the second law of thermodynamics and it wouldn't occur, be non-spontaneous. So that finishes up chapter 13, and you can finish up all the review questions and practice problems now. And you can also work all the extra practice problems and the extra practice problems. So happy thermodynamics, and we'll see you next lecture.